Hello everyone, today we're going to talk about electric field. Just like gravity, electrostatic force and gravitational force have many things in common, as you can see from last day's equation. Another one of such similarity is actually that both forces can affect objects without touching them. So therefore, we assume that gravity, any mass object with mass, is surrounded by a gravitational field that attracts other objects. And so by the same logic, we will also imagine that any charged object, for example, like a proton or electron, is surrounded by electric field. Now, electric field, so if you remember gravitational field only goes in one direction because gravity can only attract, right? But electrostatic force can both attract or repel depending on the type of charge you have in the area. So therefore, electric field is going to have more than one direction sometimes. Now, here is a picture of the electric field surrounding a charged object. So let me go to right here. So this picture right here. So this is actually a negative charge. So I'm letting you see a 3D version of this object right now. So what you're seeing, the arrows, are the electric field surrounding the object, which is pointing into the object. So this is a negative charge. So negative charge has a area electric field that points into it. Now, if I only show you one dimension, for example, only the x directions or the y, it will look something like this. Arrows that point into the charge, right? So this will be a negative charge, the electric field of a negative charge. The electric field of a positive charge, if I reverse it, will look like this. So this is the electric field for a positive charge. As you can see, there's not actually that much different, except that the arrows is now pointing away from the charges, right? So this is a proton, for example. Now, if I show you the 3D picture again, it will look like this. Okay, so you have all these arrows in every different direction, always pointing away from the charge. Okay, so this is the positive charge. So let me show you a slice again. So this is a positive charge, the electric field of a positive charge, and this is the electric field of a negative charge, like an electron. Okay, so you cannot actually see these force field. You cannot touch it. You can only imagine what it looks like. Now, so what does electric field depends on? Well, think about gravity. What does gravitational field depends on? It depends on mass of the two objects and the distance between the two objects. So electric field depends on also the distance between the two objects. So the distance from and the size of the charges, right? So if you have a very strong charge, then it will have a stronger electric field. If you have a weaker charge, then you have a weaker electric field. Actually, let me show you what does a strong and weak electric field look like. So this is let's say this is a proton, right? So proton, all the arrows should go outward. So that's the electric field. So if I increase the field strength, let me see. Okay, there we go. So increasing, let's see. There you go. So this will be a stronger charge. Like, for example, it maybe if you have like 2 or 3 or 4 protons together, it will look something like that. And this will be a weaker charge. Okay, so stronger electric field usually represented by drawing more arrows. Weaker electric field, less arrows. Okay, so let me stop that and go back to here. Okay, so electric field is defined as the electric force per unit charge. So that means electric field, which is a vector, that's why we have that little arrows on top, is the electric force per unit charge. Now, so we call from last day. So in this equation, we have to remember, okay, so right now we have E, which is not energy. This is actually electric field. Now, electric field is measured, so if you look at the unit for force, the unit for force is Newton, right? And the unit for charge is Coulomb. So therefore, not very creatively, I guess, the unit for electric field is actually Newton per Coulomb. Okay, so it's the force divided by the charge one. And then, of course, Fe is the electric or electrostatic force, which is measured in Newton. and Q is the charge of the single object, right? Of the single charge. So usually when we talk about electric field, we are looking at the electric field from one charge. Unlike force, right? Force is between two objects. Electric field is from one charge. So it's almost like temperature when you think about it. So the temperature is from, so you can think of electric field is a lot like temperature sometimes. The closer you get, the stronger it is. And the stronger the source of fire, in this case, the stronger the electric charge in the middle, the stronger the electric field is. And also, it comes from only like one source, right? Okay, so if you look at the equation, so now we can do a little bit of substitution, which is quite easy. So electric force, so let me go back here. Now, so electric force is, what is electric force? Electric force is K, Q1, Q2 over R squared. And then electric field is supposed to be that divided by Q. So it's K, Q1, Q2 over R squared divided by Q. So one of the Q is now cancelled out. So one of the Q is gone. So what you end up with is this equation for electric field, which is K, Q over R squared. Now, we have to add the same thing to this equation that we add to our force equation last time, which is this absolute value. So this equation can only get you the magnitude. So you're only using this equation to get you the magnitude. For direction, just like last time, please just use common sense. For example, positive charge should give you an electric field that goes outward. Negative charge should give you an electric field that goes inwards. So for direction, use diagram, right? Just draw like a picture of a positive or negative charge, and you should know which direction it goes toward. In the case of electric field, okay, so we are dealing with another example of a force field, which is a vector quantity. That means you lead direction. But we are not using the equation for direction. We are only using the equation to get the value of the electric field at a certain point, and then we will use the picture or diagram for direction. So in order to show this vector quantity, so what we usually to do is when we draw the electric field line, for stronger charge, we draw more line. For weaker charge, we draw less lines. But what is the electric field line actually representing? So the electric field line, so for example, if you have like a positive charge, the electric field line looks something like this, right? So like, going away from it. So all the arrow is pointing away from the positive charge. So what does that line actually mean? Okay, so the line is actually, so for example, this is a positive charge. So this electric field line that you draw on the picture is actually the direction. So physically, it does represent something. It's a direction that a positive test charge would move in the field. Now, okay, let me elaborate that a little bit. Let me actually move this charge, the one that we just joined here. I realize that I don't have enough space for myself. Let me move it down here and get myself, well, actually, I don't have to move that. There's space for that one. Okay, so I'll just draw a new one. Okay, so what does the electric field physically represent? So let's say you have a positive charge. This is a proton, right? So the electric field line looks something like this. So these are the line, these are the direction of the electric field. If you have a stronger charge, then I'll draw like more line on it. If you have a weaker charge, then that's it. Now, what does that mean is, what is a positive test charge? Positive test charge. That means if you have a little tiny positive charge, that is not the one that is giving out the electric field. So let's say you have this little tiny proton, which is a positive test charge. Okay, so now the electric field line surrounding a charge is basically the direction that this little positive guy will go. This little positive charge will go. So for example, if I put that positive charge in here, it will go to the right. Now it makes sense. It will follow the electric field and go to the right. It makes sense because these two charges repel, right? The main charge in the middle, the main blue charge is positive. My little purple one is also positive, so positive, positive repel. So it will go to the right. Now, what if I put the test charge on top of the main charge? Well, then it will go to the top. See, again, following the electric field line, right? It will always follow. So let's say I put it in here, then it will go to the top. Let's say I put it in the bottom, then it will go to the bottom. Let's say I put it like here, it will go to the lower left-hand corner. It's always going to follow the electric field line. The electric field line is basically, those lines is a prediction of where a little tiny positive charge would go if you bring it near your charge in question. Okay, so those lines tell you what happened if you have another little charge somewhere else and you place it near this one, this main one in the middle, which way will that go? So these electric field line actually tell you those direction. Now, how strong is the electric field? You have to use that equation that we just come up earlier to look for it. But usually at various different points, the further away you are, the weaker it is, right? Because if you look at the equation, it's over r squared. That means the distance. So for example, let's say you're on some location. So let's say you're maybe like somewhere over there, over here. So how strong is the electric field over here? I don't know, but I know for sure, pretty much for sure, that it's going to go this way. Right, so because if there was a little positive charge over there, it's most likely going to go to the upper right hand corner because it repels, right? So how strong is that? I don't know. Maybe in here it's going to be 10 Newton per Coulomb, but in here it's going because it's closer. The closer, the stronger it is, right? Maybe it's 50 Newton per Coulomb. So the further away you are, the weaker the electric field would be. So maybe only 2 Newton per Coulomb. But at those 3 locations though, however, like the more realistic picture should be something like this. Like strong, weaker, very weak. Like that. Right? Like that. So like these pictures. So the further away you are from it, is the weaker it becomes. Actually, right? The electric field is like that. Okay, we draw a continuous line a lot of time because it's, okay, we can't draw like hundreds of little dots like this, so that's why we draw a continuous line. But it's usually assumed that you understand the further away you are, the weaker the electric field actually is, and the direction is determined by the line. Okay, what about negative charge? So let's say you have an electron. So if you have an electron, then you're going to have a electric field that goes into the electron, like that. So for example, if the one on the right hand side is actually the electron, the one that I'm drawing right now, and the other one is a proton, then they should have exactly the same amount of field line. Because if you recall, even though proton is a lot heavier, it has exactly the same charge as the electron. It's just that it's negative. So it should have like the same, I guess, density of electric field line compared to the proton. Now, so again, the direction of the lines are what? Is the direction that a little positive charge would go if you put it near. For example, if I put a little positive charge on the north side of this negative charge, then what happened? The little positive charge, the test charge, is going to go down following the electric field. What if I put it on the right hand side right here? Then predict which way it will go. It will follow the electric field, which goes to the left. So these lines being like a mathematical concept that people use to just look at how charges can affect each other without touching is actually also a prediction of the direction that a positive test charge will go if you bring it near the charge in concept. Now, there is one thing that you have to be careful about though, which is the fact that, so let's say I have a little positive charge in here, then I should have electric field, right? So let's say its electric field is like something like this, like this, because it's a positive charge, so it's going away, Now this picture, okay, so 1 second, there's something wrong with this picture, okay? So that something wrong is over here. Electric field line in a diagram can never cross, okay? Electric field, so I will call it E field, Now later on, I'll just write E, right? You should know that it doesn't mean energy at this point. Electric field, they cannot actually intersect. Okay, can't cross. Okay, electric field cannot cross. All right, now why is it like that? Because if you have a positive charge, let's say starting from here, the little test charge, right? It will follow, remember, the positive charge follow the electric field line. So let's say the electric, you put it right here, then it will go to the top, so nothing. If you put it down here, it will go to the bottom, so nothing. But what if you put it here? It's supposed to follow the electric field line, so therefore it will arrive at this corner. But then now it has two different destinations. It can either continue to go down or it can go to the east. So which one should it follow then? Now you might say, well, just pick one. Well, this is little positive test charge is like a proton. Are you saying that proton can actually have a conscious mind that can make a decision in order so that it can decide which one it can follow this time and which one to follow next time? You are trying to, so if you think that the charge like an electron or proton can actually make a decision, then you are putting a consciousness on something that doesn't have one. So electric field line can never cross because that little positive charge has to have a destination that's predetermined from the initial condition that we put it in. It cannot result in something that it has to guess which way it goes now or which way it goes later on. Okay, so any electric field diagram that has an electric field line that are crossing is automatically wrong. Okay, all right, so we just go over an example of like an electric field question. So it's down here. Now onto the next page, right? So what is the strength of an electric field at a point that is some -2? Okay, so this is actually a mu microcoulomb. So micro something is times 10 to the power of -6. Okay, so that's the micro. It's times 10 to the power of -6. So it's divided by a million before that number is actually useful. So electric force. Okay, so how far, what is the electric field from a -2 microcoulomb charge if the electric force is this? Okay, so remember the first definition of electric field is actually electric force per charge, right? So if they give you the electric force already, which is convenient, I guess, very nice of them, times 10 to the -4, and then they give you the charge too, which is 2 times 10 to the -6 coulomb. So remember, we have to change the microcoulomb to this. Now, you notice that I also don't care about the sign. This negative sign, I don't care. They didn't even tell us where that charge is. How can we actually know which way does that electric field point? Remember, look at the picture before. The electric field can point any way that it wants, right? I don't know where. You're just telling me how far away. We're trying to find out how far away. Well, no, actually, we're just trying to find out the strength. So, for example, this charge, like for example, this location, would have the same electric field, only in slightly different direction compared to this one. Why? Because they are the same distance from the charge. I only, like, this distance is the same as that distance. If they are the same distance, then they should have the same strength of the electric field, except that it points in different direction. Okay, as long as the distance are the same, right? So in the question that we have, they never tell us anything about direction. I don't even know where the charge is or which point they want in space that they actually want to find it. So there's no point actually getting anything that's negative if it doesn't tell us directions, right? So if you put it in your calculator, you're going to get 265 Newton per Coulomb is the electric field unit. So that's that. Okay, now let's look at another one, a distance. Okay, so this one is, I hate when they do scientific rotation, when the number can just be like that, from a small charge object. So at a distance, 0.75 meter, from a small charge object, the electric field strength is that. At what distance from this object would the electric field So the electric field was originally 2.1 times 10 to the 4, and now is 4.2 times 10 to the 4. So what did we do? So the distance. So what did we do to the distance? Did we get closer or did we get further? Now go back and look at let's say this diagram again. So let's make that field string. So remember, it's the closer you get to it, the stronger the electric field. Okay, the closer you get to a charge, the closer you are to a charge, the stronger the electric field. It makes sense. The closer you get to a fire, the hotter it is, the higher the temperature. The closer you go, the closer you get to a planet or a black hole, the stronger the gravitational field, right? So the closer, so we are getting more, right? We're getting more electric field. Therefore, we're getting closer. Okay, so we know that we are getting closer. So this is, there's one way to do it is, okay, so you look at it. So there's the positive charge. Now, why do I know it's positive? Because the electric field, well, actually, I didn't know. I don't know if it's positive or negative, but I'm going to assume that it's positive right now. So we are going to have so this location right here, they said, okay, so originally is probably like this location. And it says, okay, at that location, the electric field from a positive charge should be, going away from it, right? So remember, we have all these, like, we're drawing like one of these arrows. We're drawing one of these arrows, okay? So, but we know that it is going away. Okay, so we know that it's going away from the electric, from the charge. So we know that, let's say we put it on the right hand side, then it will be going to the right. And so this is how strong. So this is the original strength, which is 21,000 Newton per Coulomb. And then we did something, which is we move closer. I don't know how close we have to move, but we did move closer. So we moved to this location, and now the electric field is stronger. Okay, well, actually, it's double. So I will draw the other arrow as double of this one. So it's 40, is now 42,000 Newton per Coulomb. Okay, so now, so which distance is the 0.75? The 0.75 is the original distance. So that's the one to the 21,000 number or value. So this is 0.75 meter. And the question is asking us for the distance to this one. Okay, so this is what we don't know. All right, so that's it. This is what we don't know. Okay, so now let me label things. I'll call this R1, R2. So this will be E1 and this will be E2. So now actually at least I have a name for everyone, right? So in this question, if you look at the electric field equation, the one with the K. So look at the electric field equation. So K Q over R squared. Now K is the constant. It's 9 times 10 to the 9, right? The Coulomb constant. So that means I can actually use, for example, location 1 to help me find out the charge, which is this value right here. So I don't actually know what the charge is. So I can use the equation 1 to position 1 to help me find out the charge. And then I'll use the charge and do a reverse question to figure out the radius. So let's see, position 1. So for position 1, we have this situation. So the electric field, which is E1, is equal to K Q1 over R1. And there's a square. So there we go. Right, K1 over R1. Now, if you put all the numbers in, you're going to get something like this. So 21,000. K is 9 times 10 to the 9. That's the Coulomb constant from the notes last time, also from the formula sheet, of course. And Q1. Now, Q1 is what we want. Actually, I don't have to call Q1. It's Q. There's only one Q in here. Like, there's only one charge in here. There's Q. There's no Q1 and Q2. There you go, Q. One charge, one Q. And then divide by the distance, which is 0.75 of a meter. Make sure you square it. Okay, so you use a calculator and try to figure out what is the amount, what is the charge amount. So then you will know how strong that charge is. So it turns out to be 1.0 1.3125 times 10 to the negative 6 coulomb. So that's microcoulomb. So about 1.3, so roughly 1.3 microcoulomb. Okay, so then we can use this and now go to position 2. Okay, so we can now go to position 2. And in position 2, we have the new electric field, same K, same Q, different R. So this times R2 square. Okay, so we do have R2. Now what we don't have is the, oh, actually we are looking for R2. So R2 right there. Okay, coming to get R2. So we have our electric field, which is 42,000 this time. K is 9 times 10 to the 9. Q is the same Q that we got, 1.3125 times 10 to the power of negative 6. Okay, so this kind of calculation is pretty tedious because number can get really, really big or really, really small sometimes. And what we're looking for is R2. And don't forget there's a square on it. Okay, so we're looking for this thing. Now, being that you're grade 12, I don't think I need to show you how to do that, right? Just swap it between the two. Oops, whoa, giant numbers. Swap it between the two and then take, get the right hand side done. Take a square root, right? Okay, so final answer. R2 is about 53 centimeters, so 0.53 meters. Okay. All right. Now, before we finish, I would just like to take a quick look on the worksheet. So, one thing that I need to remind you of is something about alpha particles. So, if you don't, now, a couple of questions in here. For example, this one, alpha particle, and I think there like another one that has an alpha particle too. Anyhow, now, so alpha particle, what is alpha particle? Don't remember? Alpha particle is actually a helium atom without the electrons on it. So the so alpha, right? So alpha particle is a helium atom without the electron. So what's a helium? A helium is 2 proton and 2 neutron, and no usually you have 2 electron. But an alpha particle is a version of the helium that doesn't have its 2 electron. So therefore, it has an overall charge of 2 plus. Okay, so it has a charge of 2 plus. Now, but it has a mass, so alpha particle, for the mass is going to be 2 proton, 2 neutron. Now, proton and neutron have approximately the same mass though. So therefore, we will say it has 4 times the mass of a single. Okay, so alpha particle should be 4 times the mass of a single proton. So a single proton weighs about 1.67 times 10 to the negative 27 kilogram. Okay, so 4 times of that is the mass of a alpha particle. Now, next thing is the charge. So what is the charge on an alpha particle? On proton, on electron, we talked about that last time, is the 1.6 times 10 to the negative 19. Now, but if you look at this thing, the alpha particle is a helium with its 2 electron missing. So it actually has 2 proton charge only. So therefore, it's not a neutral object. It has a charge, and it is 2 times the elementary charge. So 2 times the charge of a electron or proton, which is 1.6 times 10 to the negative 19. Okay, because it has 2 proton in it, and it's missing its 2 electrons, so it's no longer neutral. All right, so you need to know that for some of the question. Okay, so for example, if they say, I see, question 4 and question 6, I think are both related to alpha particle. There you go. There's another one. Okay, that's another one. So what is an acceleration? So what is the acceleration if you put an alpha particle in a space where the electric field is 76,000 Newton per Coulomb? So for look at this question, you say, okay, so we're going to have a helium, so alpha particle, right? So basically helium without the electron. Okay, so we're going to put it here. And it's being pushed by some electric field from somewhere else. Now, I don't know where that electric will come from. Maybe there's like a giant positive charge somewhere here that is giving its electric field. But we don't need to know. We just need to know that it's experiencing an electric field from someone else. Now, this electric field is this number right here. Okay, so how strong is that electric field? It's right here. Okay, and so if you look at this, so remember, like the giant positive charge in here, so it's repelling this helium, which is also a positive charge. So it's going to the right-hand side, for example, in this case, right? So therefore, the force on this object right now is going to be, now remember, we can actually look at the electric field equation and say, well, electric field is force per unit charge. So if I change that equation a little bit, then I'll have electric force is actually electric field multiplied by the charge. So EQ. Okay, so if that's the case, then to figure out how much force you're experiencing, all we have to do is to multiply the electric field that you're experiencing by the charge of yourself, which then in this case is going to be the electric field that is 76,000 Newton per Coulomb, and the charge of the alpha particle. Now that's the reason why we actually worry about this. Okay, so the charge of a particle is double the charge of a proton, which is 3.2. Okay, so this would be 3.2 times 10 to the negative 19 Coulomb, which will be roughly about 2.4 times 10 to the negative 14 Newton. So it's a very small force in this case. And then, what about acceleration? So the question is actually asking for the acceleration. So if there's a force, there must be an acceleration, right? So since this is the only force on it, this is also the net force. So in this case, net force is our electric force. And from that, remember F flat equals to ma, always. So ma is equal to the number that we just got. So 2.4 approximately times 10 to the negative 14 Newton. Okay, so to get acceleration, we need the mass of the alpha particle. That's why we have this thing. 4 times the mass of a proton. Okay, 4 times the mass of a proton. So you can continue with this question. I don't think I need to guide you through that. And then you get the acceleration, and the direction doesn't really matter. I mean, the question never gave us a diagram, so I don't know if we're actually going to the right. I totally just make up that picture, right? So that doesn't count. All right, so see you next week. That's it. I will put the homework questions on the coursework page. Okay, so goodbye, everyone.